For as long as human beings have looked up at the night sky, the stars have seemed untouchable, frozen in their remote stillness, like lanterns scattered across an infinite dome. Our ancestors imagined them as fires of gods, or as holes in the fabric of the heavens, through which divine light leaked into the darkness. When telescopes revealed that these stars were not points of light but suns like our own, the dream of reaching them took on a sharper edge. The desire to cross the abyss between the stars became not only a myth, but a possible destiny. Yet the universe hides a barrier so fundamental that it does not bend to human will. That barrier is the speed of light. The speed of light in vacuum is 299,792 kilometers per second. That number is so large, it is almost impossible to picture. Yet in cosmic terms, it is a modest limit. A beam of light can circle the Earth 7 times in a single second. It can cross the distance from Earth to the Moon in just over 1 second. But the nearest star beyond our Sun, Proxima Centauri, lies more than 4 light-years away. This means that light, the fastest traveler known to nature, requires over 4 years to reach it. For a spacecraft built by human hands, traveling at even a fraction of this velocity is unimaginably difficult. Albert Einstein revealed in 1905 that this velocity is not merely a feature of light, but a fundamental limit written into the fabric of reality. His special theory of relativity established that the laws of physics are the same for all observers moving at constant speed, and that the speed of light is the same for all, regardless of motion. It is not like the speed of sound, which can be surpassed by a jet. It is a universal constant, a boundary condition of the universe itself. No matter how hard one pushes, no matter how powerful an engine might be, nothing with mass can be accelerated to or beyond this cosmic velocity. The reason is rooted in energy. As an object approaches the speed of light, its energy requirement grows without limit. Imagine pushing a spacecraft faster and faster. At 1/10 the speed of light, the energy required is enormous but still finite. At half the speed of light, the requirement has already soared by orders of magnitude. At 9/10 the speed of light, the energy climbs to levels beyond the capacity of any conceivable engine, and as the speed approaches light itself, the energy approaches infinity. Infinity is not a large number, it is the absence of a number. It represents an impossibility. To demand infinite energy is to demand more than the entire universe contains. This is why no physical object with mass can ever reach that velocity. Along with the energy wall comes a transformation of time and space. The Lorentz transformations, the equations at the heart of relativity, show that clocks tick differently, depending on motion. As a traveler accelerates close to the speed of light, time aboard their craft slows relative to an outside observer. A journey that feels like a few years inside the ship may span centuries outside. This phenomenon, known as time dilation, has been confirmed with experiments involving high-speed particles and even precise atomic clocks flown in aircraft. It is not science fiction, it is the way the universe works. Space itself also responds. Length contraction dictates that distances shrink in the direction of travel as speed increases. To an astronaut moving close to the speed of light, the gap between stars would appear shorter than to someone watching from Earth. This effect grows more dramatic the closer one comes to the speed limit. Time and distance, once thought absolute, are pliable quantities shaped by motion. Yet this pliability is always tied to the same constraint. The speed of light remains untouchable, a wall that can never be pierced. The consequence is profound. Interstellar travel by conventional means seems doomed. Even if one could design a ship that achieved 99% of light speed, a journey to the center of the galaxy would take more than 20,000 years in the frame of Earth. The galaxy itself is 100,000 light-years across. To cross it would require spans of time greater than all of recorded human history. The dream of sailing among the stars appears to be shattered by the arithmetic of relativity. And yet, human imagination resists limits. The more rigid the wall, the more fiercely we dream of breaking it. If light speed is forbidden, is there another way? Must we move through space? Or could space itself be persuaded to move for us? This is where the concept of warp speed begins to flicker into view. It does not arise from ignoring Einstein, but from taking his equations seriously, from probing the strange elasticity of space-time that those equations reveal. If space can bend, then perhaps it can be bent in such a way that the speed limit is not broken but sidestepped. That is the seed of the warp drive. As the 20th century advanced, experiments began to test Einstein's predictions with increasing precision. Physicists watched particles in accelerators, forcing them to speeds that brushed against the light barrier. These particles behaved exactly as relativity demanded. Their masses, in a sense, appeared to increase. The faster they moved, the harder they became to accelerate further, requiring ever greater amounts of energy for ever smaller gains in velocity. None could push their cargo beyond the limit. It was as if nature had drawn a line across space-time and dared humanity to cross it. The line was not arbitrary. It was tied to the very structure of reality. Imagine space-time as a woven fabric, where every thread represents possible motion. The speed of light is the angle that marks the tightest slant a thread can take across the weave. To move faster than that is not to pull harder, but to leave the fabric altogether, to abandon the geometry that defines existence. This is why Einstein called the speed of light a constant of nature, not just a property of photons. It is a structural truth of the cosmos. For everyday life, these effects are invisible. A car on a highway or an airplane in the sky moves so slowly compared with light that the distortions of time and space cannot be detected. Yet even at modest fractions of light speed, the consequences grow significant. At 10% of light speed, time dilation is measurable, though small. At 90%, time in the traveler's frame slows to less than half the pace experienced by someone stationary. At 99%, decades in the outside world might pass while only a few years slip by on the ship. If one could hover at 99.99% of light speed, 1,000 years could flash by in the galaxy, while only a single year passed for the traveler. This raises an unsettling possibility. A ship could in principle accelerate close to the speed of light, travel for a few years in its own frame, and arrive in a distant future of the universe. In this sense, relativity grants a form of one-way time travel, but there is no way to reverse the process, no way to return to the past that was left behind. The speed of light barrier not only preserves the flow of causality, it ensures that every journey into the future comes with a price of separation from the present. For engineers and dreamers alike, the numbers are cruel. To accelerate even a small spacecraft to 90% of light speed would require energy comparable to the output of entire nations for years. To maintain such velocity would demand propulsion systems far beyond anything chemical rockets can provide. Even nuclear engines, the most powerful concept seriously studied, falter long before approaching the required thrust. Antimatter reactions, though theoretically efficient, would still confront the wall of infinite energy at the threshold of light speed. No matter the fuel, the destination remains unreachable. What makes this limit even harsher is that it is absolute for information as well as matter. No signal, no radio transmission, no flicker of causality can exceed light speed. This rule protects the logic of events, preventing paradoxes where effects arrive before their causes. Imagine sending a message faster than light to a distant world and receiving its reply before sending the original signal. Such loops would fracture the consistency of reality. Relativity locks the order of events into a universal chain, unbreakable and unbending. And yet the mind resists. We imagine what it would be like to press harder, to demand that the barrier yield. The thought experiment is intoxicating. Suppose a spacecraft could somehow exceed the light barrier. The equations of relativity suggest bizarre outcomes. Time would twist, cause and effect could reverse. Observers might see the ship arrive before it left. Its mass would become undefined, its momentum meaningless. In effect, the vessel would leave the domain of physics as we know it. It would slip into a regime that the equations cannot describe. The result is not merely difficult, it is incoherent. This incoherence is precisely why the limit must stand. Nature does not tolerate contradictions. The speed of light is not simply fast. It is the speed at which reality remains consistent. To step beyond is to invite paradox, and the universe has no patience for paradox. In this sense, the cosmic limit is both a guardrail and a law. It preserves the integrity of time, space, and matter, allowing them to exist in a way that makes sense. Still, the human spirit has never accepted barriers without searching for cracks. When faced with mountains, we learned to climb. When faced with oceans, we built ships. When faced with the air itself, we built wings of metal and flew. Now, when faced with the void between stars and the limit that defines it, our imagination strains to find an opening. The opening, if it exists, may not lie in breaking the speed of light, but in bending the road beneath it. Einstein himself provided the hint. His later theory, general relativity, showed that space-time can curve, stretch, and compress under the influence of mass and energy. If space can bend, could it not also be bent in ways that mimic faster than light motion? Could the traveler remain subliminal in their own frame, while the universe around them shifts, like a wave carrying a surfer to shore? This is the thread of thought that will eventually lead to the idea of warp. But before that vision can be explored, we must confront one more truth. Even if space can be bent, bending it requires energies and substances that challenge imagination. The speed of light is not merely a wall, it is a fortress guarded by mathematics. To approach it is to discover not freedom, but deeper mysteries. And yet, those mysteries are precisely what make the dream of surpassing the cosmic speed limit so irresistible. The most striking element of Einstein's vision is how something so simple can change everything. The postulates of special relativity are brief. First, the laws of physics are the same in all inertial frames. Second, the speed of light in vacuum is constant for all observers. From these two statements flows the entire structure of modern physics. Time dilation, length contraction, mass-energy equivalence, all emerge from these cornerstones. The universe is not built on hidden gears or ethereal forces, but on the geometry of space-time itself. A geometry that bows to these laws without exception. Consider a simple image. A flashlight beam leaves Earth and races outward at light speed. A spacecraft follows behind at 90% of light speed. One might imagine that from the ship's view, the beam would crawl away slowly, only 10% faster. Yet relativity demands otherwise. The beam still speeds away at light speed, no matter how fast the ship is traveling. The mathematics rearranges time and distance so that the constancy holds true. Space contracts, clocks dilate, perceptions twist, but the speed of light remains unchanged. It is as though the universe conspires to preserve this limit, reshaping itself in any way required to maintain it. This constancy is what makes relativity so strange to common sense. Human intuition is trained in a slow world where velocities add in familiar ways. If a person walks inside a moving train, their speed adds to the speed of the train. But at cosmic scales, addition ceases to apply. Light's velocity does not stack or subtract. It stands alone, immune to arithmetic. The result is a cosmos far stranger than intuition suggests. A cosmos where time itself is malleable, yet anchored by this one absolute. The price of this cosmic order is isolation. Stars remain far, not only in distance, but in duration. Even the nearest neighbors are separated by spans that human lifetimes cannot bridge. A civilization bound to subliminal travel must measure its explorations in generations, perhaps in millennia. Dreams of rapid journeys across the galaxy collapse under the arithmetic of the light barrier. The vastness of space is no longer simply a question of distance, but of time itself, stretching before us like an ocean we cannot cross. And yet, even within this confinement, there is wonder. The very laws that bind us also open paths of discovery. Without relativity, we would not have nuclear power, GPS navigation, or the precise understanding of cosmic evolution. The same equations that forbid faster than light travel also explain how stars shine, how black holes form, how the universe expands. The speed of light barrier is not an enemy but a teacher, showing us the deep coherence of nature. Every experiment that confirms it is another proof that the cosmos is intelligible, that reason can uncover its secrets. Still, the imagination stirs. Suppose the light barrier cannot be broken, but could it be bent? Suppose one does not move faster than light, but instead moves differently, carried by distortions in the very geometry of space. Einstein's general theory of relativity, unveiled in 1915, provides the seed of this thought. It describes how mass and energy tell space-time how to curve, and how curvature tells matter how to move. From this dialogue between matter and geometry arise planets in orbit, light deflected by stars, the slow dance of galaxies. If geometry can be shaped by mass and energy, could a civilization one day shape it deliberately? Could they sculpt space-time into a wave and ride it, like a surfer, across the cosmic sea? This is no longer a question of speed, but of perspective. To an outside observer, the bubble of curved space might appear to leap faster than light. Yet inside the bubble, the traveler would drift serenely, never breaking the limit in their local frame. The laws of relativity would remain intact, yet their consequences would be transformed. This possibility is not a dismissal of Einstein, but an embrace of his deepest insight, that space-time is not fixed, but pliable. Such speculation edges us toward a new chapter in the story. From the cold arithmetic of the cosmic speed limit, we turn toward the audacity of human imagination. Science fiction has long played with the idea of warp speed, hyperspace, and instantaneous jumps across the stars. For much of history, these were only tales. But with relativity's revelations, the tales took on a strange credibility. Perhaps fiction had glimpsed a path that equations would later outline. Perhaps the barrier of light speed was not the end of the story, but the beginning of another. Thus, the chapter closes with a paradox. The speed of light is unbreakable, yet it is also the very clue that inspires dreams of breaking free. The cosmos enforces its law with rigor, yet it leaves just enough room in its equations for imagination to slip through. The stars remain impossibly far, yet the thought of reaching them refuses to die. The cosmic speed limit is both a wall and a window. Beyond it lies the unknown, and into that unknown humanity is destined to gaze, searching for a way forward. Even as science declared the speed of light untouchable, stories refused to listen. Long before Einstein, human imagination was already racing through the heavens. Ancient myths spoke of gods who leapt across the sky in a single stride, or spirits who rode chariots of fire from star to star. These were not scientific concepts, but reflections of longing. The same longing that still burns whenever we gaze into the dark expanse overhead. When the telescope revealed that the stars were suns, each perhaps with its own worlds, the dream of travel beyond Earth took on new intensity. The universe no longer seemed an unreachable canopy. It became a frontier, and the human mind does not rest when confronted with a frontier. Science fiction gave that longing a voice. Writers imagined voyages across interstellar gulfs with the ease of ocean travel. They pictured engines that hummed with power, ships that leapt from one system to another in the blink of an eye. In the middle of the 20th century, as rockets carried astronauts into orbit, stories grew bolder. The television screens of the 1960s showed starships gliding at warp speed, pushing past the laws of physics with elegance and style. Audiences accepted it not because they misunderstood science, but because they wanted to believe that science could one day be bent toward that destiny. The dream was not limited to one culture or one generation. In novels and films, across decades, the motif repeats. A vessel leaves Earth, engages some mysterious drive, and arrives at a starlight years away, as though the cosmos itself had become a highway. The names differ: warp speed, hyperspace, jump drives. But the yearning beneath them is the same. Fiction creates the maps that physics has not yet drawn. These maps may be built of metaphor rather than mathematics, but they shape the imagination of the very scientists who later return to equations with questions inspired by those tales. Why is the desire so strong? Because interstellar space is vast beyond measure. The nearest star is 4 years away, even at light speed. The nearest truly Earth-like planet may be dozens or hundreds of light years distant. Our galaxy, a spiral of 200 billion suns, stretches 100,000 light-years across. Even the most ambitious visions of conventional rocketry falter under such scales. A chemical rocket, like the ones that carried astronauts to the moon, would take tens of thousands of years to reach even the nearest stars. Nuclear propulsion, more powerful but still bound by fuel limits, would cut the time only to thousands of years. These numbers are longer than all of recorded history. They make interstellar colonization seem hopeless if we are bound by known propulsion alone. Thus, fiction fills the gap. Where engines fail, imagination supplies wings. To cross the void in a single lifetime, one must leap beyond relativity itself. Stories of warp and hyperspace are not childish fantasies but symbolic solutions to a real problem. They express a deep truth, that humanity is not content to remain a planetary species forever. The stars call, and the call is louder than any calculation. Science fiction became the language of that call, whispering that perhaps the cosmos holds secrets yet undiscovered, ways to cheat the limit without breaking it, ways to bend the rules without shattering them. And in the late 20th century, a remarkable thing happened. The speculation of fiction collided with the rigor of physics. A young Mexican physicist, Miguel Alcubierre, inspired by the warp drives of television, asked whether Einstein's equations might allow something similar. Could space-time itself be manipulated to mimic faster-than-light travel while preserving relativity's laws? He found, to the astonishment of many, that the mathematics answered yes. What had begun as myth passed into fiction, now pressed into the realm of theory. The dream of faster-than-light travel was no longer only a story. It had acquired an equation, but before Alcubierre, there was only the longing, only the persistent echo of an idea repeated across cultures and generations. The longing itself deserves attention. Why do we reach for the impossible? Perhaps because the impossible forces us to grow. When the horizon stretches beyond sight, we imagine paths that reason denies. And sometimes, those paths reveal truths reason had not yet seen. The 20th century brought rockets that clawed their way into orbit and probes that slipped beyond the planets. But the scale of their achievements revealed the scale of the problem. Voyager, one of humanity's most successful spacecraft, launched in 1977 and now sails at over 60,000 kilometers per hour relative to the Sunday. This is faster than any human-built object in deep space, a velocity that would carry a car around the Earth in less than 40 minutes. Yet even at this staggering pace, Voyager would require more than 70,000 years to reach the nearest star. The numbers crush the dream before it can rise. When the Apollo missions set foot upon the Moon, many imagined Mars would follow within decades, and the outer planets soon after. But the reality of distance proved otherwise. Even Mars, at its closest, requires months of travel with enormous expenditures of fuel. The gulf between planets is immense, and the gulf between stars is greater by orders of magnitude. The rockets of chemical fire that lifted humans from Earth are useless for interstellar ambitions. The physics is merciless. The propellant mass grows to impossible levels. The journey times stretch beyond generations. A child born on a ship bound for Proxima Centauri would die long before arrival, and so would her descendants, with only some remote future lineage reaching the destination. Science fiction answered this despair with invention. If conventional speed was not enough, then there must be another kind of motion. Hyperspace, warp corridors, wormhole shortcuts, all appeared in the pages of novels and flickered across screens. These were not idle fantasies but psychological lifeboats, carrying the imagination across gulfs that technology could not yet bridge. To envision starships leaping between systems in an instant was to refuse resignation. It was to keep the stars within reach, if not yet in fact, then in story. And the stories mattered. A generation of scientists who would later probe relativity and quantum theory grew up watching and reading such tales. They saw warp drives on glowing screens, and while they knew the science said no, the question lingered. Could there be a loophole? Could Einstein's cosmic wall have a hidden door? This is the power of fiction. It does not always predict, but it inspires. It does not dictate what science will discover, but it points to what science longs to seek. The cultural weight of faster-than-light travel is immense. It is not only about exploration but about survival. Our sun will not burn forever. In billions of years it will swell and die. Long before that, asteroids, comets, or our own excesses may threaten life on Earth. To imagine humanity without a path to the stars is to imagine confinement in a fragile cage. Faster-than-light travel, in this sense, is not just an adventure. It is a promise of continuity, of escape, of becoming a species that can endure the trials of cosmic time. Even if the mathematics denies it, the psychology demands it. Yet fiction has also shaped expectation in ways that physics cannot match. Audiences conditioned by tales of warp often underestimate the severity of the light barrier. They see a ship vanish into hyperspace and assume that the problem is simply one of engineering, but the truth is harsher. Relativity is not a set of technical hurdles, but a fundamental law. No clever trick of propulsion, no stronger engine, no denser fuel will push a vessel beyond light speed. The only possible path lies in bending the fabric of space-time itself, in using geometry rather than thrust. This is why Alcubierre's idea was so shocking. It did not propose a faster engine, it proposed a different kind of motion altogether. But before his equations, before his warp bubble, there was only the dream itself. And dreams are powerful. They sustain curiosity across decades. When progress is slow, they carry scientists into fields where answers may hide. They preserve the sense of wonder that fuels inquiry. Without the dream, there would have been no question. Without the question, there would have been no answer, however partial. The dream of faster-than-light travel is therefore more than fantasy. It is the seed from which real science has already sprouted. The collision between dream and reality is where the story turns next. When the mathematics of relativity met the imagination of fiction, the result was something neither realm had foreseen. Out of this collision emerged the idea that space itself could be warped, and that within this warping, a loophole in the cosmic limit might exist. The dream began as myth, evolved into story, and then transformed into speculation grounded in equations. The stars were still impossibly far, but the path to them had acquired a glimmer of plausibility. The persistence of the faster-than-light dream reveals something about human nature. We are a species that refuses confinement. Each horizon we encounter becomes a challenge, not a prison. When early explorers saw the edge of the ocean, they did not stop. They built ships and crossed it. When mountains rose against them, they found passes or carved tunnels. When the sky itself seemed unreachable, they invented wings of canvas, then of metal, then engines that shattered the sound barrier. The dream of interstellar travel is simply the next horizon, magnified to scales beyond imagination. It is not surprising that stories grew around it, for stories are the sketches of futures not yet built. But stories are not only about technology, they are about the human need to believe that the impossible may one day become possible. In fiction, warp drives are often engaged with the press of a button, a hum of power, and a streak of stars across the screen. These dramatizations conceal the terrifying complexity of what such a leap would demand. Yet they also serve an important role. They normalize the idea that faster-than-light travel belongs in the realm of human possibility. They whisper that if it can be imagined, it can perhaps be achieved. This whisper has power. Many great advances were once dismissed as fantasies. The notion of heavier-than-air flight was ridiculed until the Wright brothers proved otherwise. The idea of splitting the atom seemed absurd until fission was demonstrated. Space travel itself, only a century ago, was the province of dreamers and visionaries. Fiction does not guarantee reality, but it prepares the mind to accept it when reality shifts. Without the constant drumbeat of faster-than-light stories, the idea might never have been tested against equations at all. Yet the gap between dream and physics is immense. For most of the 20th century, physicists accepted that faster-than-light travel was impossible. The speed of light barrier seemed absolute. While science fiction danced across the stars, science itself remained grounded in subliminal propulsion, struggling even to extend human presence to Mars. The contrast was sharp and sometimes discouraging. Engineers who worked on rockets knew the limits better than anyone, They calculated propellant requirements, energy costs, and journey times. They saw the hopelessness of conventional methods. Yet perhaps because of this hopelessness, the allure of unconventional methods grew stronger. If no normal engine could carry us to the stars, then perhaps an abnormal one could. This is where imagination serves science most directly. By refusing to surrender to despair, fiction kept the faster-than-light dream alive, long enough for theory to catch up. In 1994, Miguel Alcubierre asked a question no one had posed with full seriousness before. What if a spacecraft did not move through space at all, but instead bent space itself? Could the fabric of space-time be manipulated in such a way that a bubble of distortion carried a vessel across the cosmos faster than light relative to outside observers, while the vessel inside never actually exceeded light speed in its local frame? The mathematics of general relativity, which Einstein had given the world nearly 80 years earlier, provided a startling answer. It was possible in principle. The warp drive was no longer only a trick of fiction. It had become a solution within the equations of physics, even if it remained wildly impractical. Alcubierre's work did not break relativity. It used relativity's deepest insights, the pliability of space-time, to sidestep the cosmic speed limit. The dream had gained its first foothold in science. This transition marks a turning point. Before Alcubierre, faster-than-light travel was the domain of storytellers, a canvas for hope and spectacle. After Alcubierre, it became a legitimate subject of theoretical physics, however speculative. The bridge from myth to mathematics had been built, slender and fragile, but real. Humanity's longing for the stars had found its echo not only in stories but in the geometry of space-time itself. The dream of faster-than-light travel persists, not because it is easy, but because it is necessary. It embodies the refusal to accept that the stars will remain forever out of reach. It transforms impossibility into challenge, and it reminds us that imagination and science are not enemies but partners, each feeding the other. Fiction dared to ask the question. Physics dared to answer. Now, as we step into the next chapter, we must confront what that answer demands. For to warp space itself is to wield energies and forces that strain belief. The dream has become an equation, but the equation carries a cost. In 1994, a young physicist in Mexico named Miguel Alcubierre sat down to ask a question that seemed closer to science fiction than to science. He had been watching starships leap across the galaxy on television, and though he knew that relativity forbade such travel, he wondered if the equations themselves might hold a hidden path. General relativity is not a book of prohibitions, but a language describing the curvature of space-time. Perhaps within that curvature lay a loophole. Alcubierre opened Einstein's field equations, not as a skeptic, but as a dreamer with a pen, and to his astonishment, the mathematics gave an answer. The answer did not describe a starship that outran light. It described a pocket of space-time itself, a bubble that could contract space in front of it and expand space behind it. The vessel within this bubble would remain still, relative to its local surroundings, never exceeding the light speed limit in its own frame. Yet from the outside, the bubble could appear to move faster than light, carrying the ship within it across interstellar gulfs in times far shorter than relativity seemed to allow. In essence, the ship would not move through space at all. Space itself would move, and the ship would ride the distortion, like a raft on a river. This was the Alcubierre drive, a concept that stunned the physics community. It did not violate relativity, it exploited it. The cosmic speed limit applied only to local motion through space-time, not to the motion of space-time itself. After all, the universe had already revealed its willingness to expand. Galaxies drift apart as space stretches between them. The expansion can occur faster than light over vast distances, and yet no law is broken because nothing is moving locally faster than light. Alcubierre realized that if cosmic expansion could separate galaxies, perhaps artificial expansion and contraction could move a spacecraft. The warp bubble he described was elegant in theory. Imagine a sphere surrounding a ship, Ahead of the sphere, space-time compresses, drawing the destination closer. Behind it, space-time expands, pushing the origin away. The bubble itself drifts across the universe, carrying its contents untouched. Inside the bubble, crew and passengers would feel no acceleration, no crushing forces. They would simply drift in free fall, while the universe outside shifted around them. From their perspective, the stars would race past, yet they would experience no violation of physics. The beauty of Alcubierre's solution lies in how it reframes the question. Instead of asking how to push matter faster, it asks how to sculpt the medium in which matter resides. It is like ceasing to row across a river, and instead shaping the river itself to carry you downstream. The mathematics of general relativity, with its intimate link between energy, mass, and curvature, provides the framework for such sculpting. What Alcubierre did was to write down a metric, a description of space-time geometry that allowed for such a bubble to exist. The metric satisfied Einstein's equations. It was mathematically valid, but mathematics is not engineering. A valid solution to Einstein's equations does not guarantee that nature permits it. When Alcubierre published his paper, physicists immediately asked, what kind of energy would be required to create such a bubble? The answer was troubling. The equations demanded negative energy density, a form of matter or energy unlike anything known in ordinary physics. Negative energy is not just exotic, it is antithetical to our experience. All familiar forms of energy, from sunlight to nuclear reactions, are positive. To bend space in the way Alcubierre described seemed to require substances that might not exist in usable quantities, if at all. Still, the idea could not be ignored. It had taken the fantasy of warp drives and placed them within the architecture of real physics. Even if the requirements were absurd, the principle had been established. Faster than light travel might not be forbidden after all. It might simply be difficult beyond present imagination. The line between fiction and science had blurred. A concept born from a television show had looped back into equations, and those equations had affirmed that the dream was not incoherent. The door was not open, but it was no longer locked. Alcubierre himself was cautious. He did not claim to have invented a practical engine. He had written down a solution, a possibility. Whether the universe allowed it in practice was a question for further generations. But by writing those equations, he changed the conversation. No longer could one dismiss warp drives as pure fantasy. They had become a topic of theoretical research. Papers multiplied. Physicists debated the meaning of negative energy, the role of quantum effects, the potential refinements that might reduce the impossible energy costs. The Alcubierre drive became not a blueprint, but a beacon. The essence of Alcubierre's insight can be imagined in simple terms, though the equations that describe it are anything but simple. Picture space as a vast fabric stretched in every direction. A spacecraft, bound by relativity, cannot rip through the fabric faster than the threads allow. But the fabric itself is not fixed. It can bend, ripple, and stretch. The universe already shows us this flexibility in the way galaxies recede as space expands. That expansion can proceed faster than light, without contradiction, because no galaxy is moving locally faster than light. It is the metric of space itself that evolves. Alcubierre's bubble was an attempt to capture this cosmic phenomenon and apply it on a smaller scale, not to entire galaxies but to a region surrounding a single ship. In the metric he proposed, space in front of the bubble contracts. Distances ahead shrink, drawing the destination closer with each passing moment. Behind the bubble, space expands, stretching the origin away. The combination propels the bubble forward. To an external observer, the bubble may appear to exceed light speed. To the occupants within, nothing unusual happens at all. Their clocks tick normally, their bodies feel no strain, their ship floats as though in calm waters. They do not move through space. Instead, space moves for them. This distinction is vital. Relativity forbids motion faster than light through space-time, but it does not forbid space-time itself from rearranging. The same mathematics that describes black holes bending space into wells and the universe stretching across eons can also describe a localized wave that carries a craft. It is like a surfer riding a swell. The surfer moves with the wave, not faster than the water molecules themselves. Yet from the shore, it can seem as though the surfer is racing far faster than the flow beneath. The idea captivated scientists and the public alike because it showed how science fiction could return to science with unexpected rigor. Here was a real physicist, using Einstein's own equations, describing something that sounded like warp speed. The excitement was tempered, however, by the immense challenges that emerged when the solution was examined more closely. The bubble required negative energy density, something entirely outside the catalogue of known matter. Negative energy is not the same as simply having less energy than normal. It implies a reversal of behavior, a region of space-time where the energy conditions that normally stabilize the universe are inverted. Physicists had glimpsed hints of negative energy in quantum theory. The Casimir effect, in which two closely spaced plates experience an attractive force due to quantum fluctuations, can be described as a kind of negative energy density in the vacuum between them. But this effect is vanishingly small, detectable only in laboratories with exquisite sensitivity. To inflate a warp bubble of even microscopic size would require negative energy on scales far beyond what the Casimir effect could provide. The numbers quickly leapt to absurd magnitudes, demanding not kilograms or tons of exotic matter, but amounts rivaling the energy output of entire galaxies. Yet even as the practicality crumbled, the conceptual shift remained profound. The Alcubierre drive reframed the conversation. It reminded physicists that relativity is not a closed door, but a landscape of possibilities. The speed of light limit, once seen as absolute confinement, became instead a contour in the geometry of space-time. One could not cross it directly, but perhaps one could flow around it, as rivers flow around stones. This subtle change in perspective reinvigorated research into exotic spacetimes, wormholes, and quantum effects that might enable new forms of travel. Critics pointed out that the warp bubble, even if it could be created, carried paradoxes of its own. How would one steer such a bubble from within, since the interior is causally disconnected from its boundary? How would a ship inside the bubble communicate with the universe outside? If the bubble moved faster than light relative to the stars, then signals could not escape forward to control or navigate. These problems revealed that Alcubierre's solution, while mathematically sound, was incomplete as a practical mechanism. It was a sketch of possibility rather than a detailed plan. Nevertheless, the sketch was enough to shift the horizon of thought. The dream of faster-than-light travel, once the exclusive domain of fiction, now stood with one foot in science. Equations had legitimized the idea. Even if the path remained blocked by monumental obstacles, the mere fact that relativity allowed such a geometry was astonishing. It meant that the universe, at least in theory, did not prohibit what had once seemed impossible. The line between no and maybe is vast, and Alcubierre had pushed humanity across it. As word spread, the Alcubierre drive captured imaginations worldwide. Physicists debated its implications at conferences. Popular science magazines printed diagrams of warp bubbles. Artists drew sleek ships nestled in glowing distortions of space. The phrase warp drive, once belonging solely to fiction, now appeared in scientific journals. It was a reminder that sometimes imagination must lead and mathematics must follow, and together they reveal landscapes neither could have discovered alone. The Alcubierre drive occupies a strange place in the history of physics. On one hand, it is a mathematical curiosity, a solution drawn from the elegant yet merciless equations of general relativity. On the other hand, it is a symbol, a proof that the dream of faster-than-light travel has not been banished entirely to the realm of impossibility. The solution showed that within the flexible geometry of space-time, new forms of motion can exist, yet it also exposed the profound cost of bending the cosmos to human will. When Alcubierre's paper was first circulated, reactions ranged from astonishment to skepticism. Some physicists marveled at the audacity of turning Einstein's equations against the very barrier they enshrined. Others dismissed the idea as impractical, pointing to the enormous negative energy requirements. But none could deny that the solution was valid in a strict mathematical sense. It was not pseudoscience, not fantasy scribbled in the margins, but a real geometry of space-time, written with the same symbols that describe black holes and cosmic expansion. The warp bubble had entered the language of serious discussion. The very structure of the bubble raised profound questions. If space-time could be shaped in such a way, what else might be possible? Wormholes, another theoretical solution to Einstein's equations, had already hinted at shortcuts through the cosmos. The Alcubierre drive offered a different kind of shortcut, one that did not tunnel but surfed. Both required exotic forms of matter and energies beyond imagination, yet both demonstrated that relativity is more permissive than once thought. The cosmic speed limit was still there, but its context had changed. It was no longer a wall, but a landscape of alternative paths. Inside the bubble, the ship would feel nothing unusual. It would not accelerate. No engines would roar. No crew would be pressed back into their seats. Instead, the surrounding space would shift, carrying them as though in a pocket of stillness. To an external observer, the bubble might streak across the galaxy at apparent superluminal velocity. To the crew, the trip might feel no different from drifting in orbit. The paradox of calm within and speed without was part of what made the concept so alluring. It suggested that if the laws of geometry could be mastered, travel across light years could become as smooth as sailing a quiet sea. But mastery of geometry requires mastery of energy, and here the dream stumbles. The equations revealed that the warp bubble could not exist with ordinary matter. It demanded negative energy densities of staggering magnitude. Negative energy is not a substance that can be scooped from space. It is a delicate quantum phenomenon, glimpsed in fleeting laboratory effects, always small, always fragile. To inflate a bubble large enough to contain a spacecraft would require more negative energy than exists in the observable universe. This realization tempered the excitement. The solution was real, but the scale was monstrous. Even so, the fact that the solution existed changed the psychology of the question. Before Alcubierre, faster-than-light travel was easy to dismiss with a simple statement: relativity forbids it. After Alcubierre, the dismissal was less certain. Relativity did not forbid it. It allowed it, under conditions that were currently impossible. The shift from impossible to impractical may seem small, but in science it is immense. Impractical problems invite ingenuity. Impossible problems invite only despair. The Alcubierre drive thus became a catalyst. Physicists began exploring refinements that might reduce the energy requirements. Some suggested modified bubble geometries that required less negative energy. Others proposed connections with quantum field theory, searching for loopholes in the energy conditions. None solved the core problem, but each attempt deepened understanding. Research into exotic spacetimes grew more serious. The warp bubble became a thought experiment that sharpened the edges of theory, testing what relativity could and could not tolerate. For the public, the symbolism was even greater. The phrase warp drive no longer belonged exclusively to the realm of starships on screens. It had been stamped with the legitimacy of physics. Headlines announced that faster-than-light travel was not entirely fantasy. Although the caveats were immense, the spark was undeniable. Humanity had taken one step closer to the dream, if only in thought. The idea that equations might someday guide us across the stars felt less like myth and more like destiny. Yet destiny is not given, it is forged. The Alcubierre drive did not solve the problem of interstellar travel. It illuminated it. It showed that the path forward would not be a matter of stronger rockets or denser fuels. It would require control over space-time itself, mastery of energies so alien that even naming them feels speculative. In doing so, it reframed the quest for faster-than-light travel as not merely technological but fundamental. The stars will not be reached by thrust alone. They will be reached, if ever, by rewriting the fabric of the cosmos. As this chapter closes, the exhilaration of Alcubierre's breakthrough gives way to the shadow it casts. The warp bubble may be permitted by relativity, but it comes with demands that dwarf comprehension. To imagine harnessing enough negative energy to drive such a distortion is to imagine commanding forces greater than galaxies. The dream survives, but it carries a cost measured not in fuel tanks or engines, but in the very structure of existence. And so the story turns. The Alcubierre drive opened the door, But on the other side waits the question of price. How much energy does it take to bend the universe? Can negative energy be found in quantities sufficient to sculpt space-time? Or is the warp drive a mirage, luring us toward a horizon that recedes forever? These questions lead directly into the next chapter, where energy barriers rise like mountains, daring us to climb or forcing us to turn back. The Alcubierre drive was dazzling in theory, but theory has a way of demanding tribute. The tribute, in this case, was energy. When physicists began to calculate how much energy would be required to inflate and sustain a warp bubble, the results were breathtaking in their impossibility. The numbers soared far beyond any human capacity, far beyond even the capacity of stars. The dream of warp speed had been legitimized by mathematics, but it was shackled by the most brutal of costs. The equations indicated that the bubble could not be formed with ordinary matter or energy. It required negative energy density, something entirely alien to our everyday experience. In familiar physics, energy is always positive. A photon of light carries positive energy. A nuclear explosion releases positive energy. The food we eat, the fuels we burn, the electricity that lights our cities, all represent positive quantities of energy stored and released. Negative energy, by contrast, is a strange reversal. It is not simply a deficit, like owing money. It is energy that behaves in the opposite way, bending space-time contrary to normal expectations. To form the bubble, negative energy must surround the craft, forming a kind of shell that shapes space ahead and behind. Without this exotic material, the bubble collapses into meaninglessness. Alcubierre's equations were clear. The geometry was mathematically sound, but only if space-time could be fed with a substance no one had ever gathered in usable form. The concept of negative energy exists in quantum physics, in the subtle fluctuations of the vacuum, where particles and antiparticles flicker into existence and vanish. In these fluctuations, regions of negative energy can appear briefly, balanced by regions of greater positive energy elsewhere. But these effects are tiny, measurable only with the most delicate experiments. They are whispers of possibility, not oceans one could sail. The scale required for a warp bubble is overwhelming. Estimates suggested that to move a small spacecraft, the amount of negative energy needed would equal the mass energy of the entire observable universe. To imagine this is to confront absurdity. The combined energy of every galaxy, every star, every planet, all the light that has ever shone, all the matter that has ever burned, would be insufficient to inflate a single bubble large enough to hold a ship. The dream had found its price, and the price was everything. This revelation did not end the discussion, but it shifted its tone. Alcubierre's drive had proven that relativity did not forbid faster than light travel, but relativity also revealed how fiercely nature guarded the door. The energy requirement was not a simple barrier to engineering, not a matter of waiting until better engines arrived. It was a fundamental roadblock, a challenge that mocked imagination itself. Physicists began to search for refinements, ways to reduce the requirement from infinite to enormous, and from enormous to at least conceivable. Each refinement carved a little from the mountain, but the summit remained impossibly high. Still, there was a glimmer in the darkness. Quantum effects, such as the Casimir effect, hinted that negative energy was not entirely fiction. The Casimir effect, first predicted in the 1940s and confirmed experimentally, arises when two metal plates are placed very close together in a vacuum. The quantum fluctuations of the vacuum between them are restricted, leading to a measurable, attractive force. This force can be interpreted as arising from a region of negative energy between the plates. It is tiny, far too small to power a warp bubble, but it is real. And in physics, reality often begins with small cracks in impossibility. The paradox deepened. The warp drive was not forbidden, but it demanded resources no civilization could hope to command. Negative energy existed in principle, but only in quantities too small to notice except in laboratories. The challenge was no longer one of equations but of nature itself. Could the laws of quantum fields ever be harnessed on scales vast enough to curve spacetime for travel? Or would the warp bubble remain a ghostly possibility, forever unreachable? The first response to the monstrous energy requirements was disbelief. Surely there must have been an error, a miscalculation hidden in the mathematics. But as more physicists checked the equations, the verdict remained the same. The warp bubble was mathematically sound, but demanded an ocean of negative energy so vast that no conceivable civilization, not even one spanning galaxies, could ever provide it. If warp speed was possible, it seemed to be a cruel joke of nature, teasing humanity with equations, only to drown the dream in unreachable numbers. Yet physicists are not easily discouraged. Once the equations existed, the hunt for refinements began. Could the geometry of the bubble be altered to require less negative energy? Could the structure be reshaped so that space-time bent more efficiently, reducing the cost of distortion? Researchers explored variations of Alcubierre's metric, adjusting parameters, compressing the bubble, changing its thickness. Each adjustment carved away some fraction of the requirement. From a universe of energy, the demand dropped to galaxies, from galaxies to stars, from stars to perhaps the total mass energy of a planet. These were still astronomical amounts, but at least they no longer mocked comprehension itself. One proposal suggested that if the warp bubble were made extremely thin, its energy cost might fall by many orders of magnitude. Instead of surrounding the ship with a thick shell of distortion, a razor-thin boundary might suffice. Another refinement involved altering the shape of the bubble from spherical to more complex geometries, changing how space contracted and expanded. In every case, the mathematics bent slightly, offering glimpses of feasibility, though never approaching practicality. The numbers remained vast, but not infinitely vast. And in physics, that shift can mean everything. At the same time, the search for negative energy continued in the quantum domain. The Casimir effect was proof that quantum fields allow such phenomena, but could they be amplified? Some theorists proposed using squeeze states of light, special quantum configurations, where fluctuations in energy could dip below zero in controlled ways. Others speculated about vacuum fluctuations near black holes or in regions of intense gravitational curvature, where exotic effects might be magnified. None of these ideas approached the scale required, but they revealed that negative energy was not merely an artifact of mathematics. It was woven into the fabric of quantum fields, however delicately. There was also a deeper question: would the universe permit large amounts of negative energy at all? Quantum field theory imposes limits known as energy conditions, rules that ensure stability of space-time. Violating these conditions on large scales might lead to paradoxes or instabilities. Some physicists argued that the warp bubble might collapse under its own contradictions, prevented not by lack of imagination, but by deeper laws of consistency. Others countered that until a full theory of quantum gravity was achieved, such prohibitions could not be proven. The debate reflected a truth about frontier physics. Sometimes the boundary between impossible and unknown is razor-thin. Even with refinements, the energy problem remained daunting. Estimates shrank from universe-sized to planet-sized, but even a planet's worth of energy is far beyond reach. To harvest such energy would require dismantling worlds, tapping into stellar cores, or mastering antimatter production at inconceivable scales. Civilization today struggles to produce grams of antimatter at enormous cost. To imagine fueling a warp bubble with planetary energy is to leap beyond centuries into epochs of technological development. The scale itself became a mirror, reflecting not only the ambition of physics but the limits of civilization. Yet the very act of exploring these refinements had value. By searching for ways to reduce the energy requirements, physicists probed the edges of relativity and quantum theory. They asked what space-time could tolerate, what quantum fields could provide, and what the laws of energy truly forbid. Even if the warp bubble never leaves the page, it functions as a laboratory of thought, a place where the rules of physics are tested to their breaking points. And often, testing rules reveals new insights, even if the original dream slips away. The story of energy barriers, then, is not only about frustration, but about persistence. The dream refuses to die because each step, however impractical, sharpens understanding. To reduce the energy from infinite to enormous is already a form of progress. It suggests that impossibility may not be absolute, that barriers may soften under the pressure of ingenuity. The warp bubble may remain beyond us, but the path of inquiry it opened leads into deeper mysteries of energy, matter, and space-time itself. The deeper physicists pressed into the problem of energy, the more the dream of warp revealed its dual nature. It was both liberating and imprisoning. Liberating because relativity itself did not forbid the bubble. Imprisoning because the bubble's demands reached heights that mocked imagination. To travel among the stars by bending space-time was not ruled out by nature, but it was locked behind a gate whose key seemed forever out of reach. The energy barrier became the true frontier, more forbidding than the cosmic speed limit itself. Some researchers speculated that future theories might change the landscape. Our understanding of physics is not yet complete. General relativity describes the large-scale curvature of space-time with extraordinary precision, while quantum mechanics governs the microscopic realm with equal success. But the two theories do not yet merge into a single framework. The long-sought theory of quantum gravity may one day reveal new possibilities for energy and space-time. Perhaps negative energy is more accessible than we think, or perhaps the structure of the vacuum itself hides reservoirs that could be tapped. Until that unifying theory is written, the final verdict on warp remains suspended. Others turn their attention to dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy pervades space itself, pushing galaxies apart as though space-time were inflating under an invisible hand. Its nature remains uncertain. Is it a property of the vacuum? A field woven into the fabric of existence? If dark energy could be understood and controlled, it might serve as the raw material for bending space. The expansion of the universe is proof that space-time can be manipulated on cosmic scales. The question is whether such manipulation can be localized and directed. If the cosmos can accelerate galaxies, could a civilization one day accelerate a ship? Even in speculation, caution is necessary. Energies of this scale may bring consequences as dangerous as they are wondrous. To command negative energy or to shape dark energy may invite instabilities that collapse the bubble or tear space-time itself. The same equations that allow the bubble also hint at catastrophic risks, like horizons forming around the ship that trap signals or distort causality. To approach such forces would be to stand at the edge of a volcano, seeking to channel its fire without being consumed. The dream of warp is therefore shadowed not only by impossibility, but by danger. The persistence of the dream, however, reflects something more than technical curiosity. It reflects humanity's refusal to accept confinement. The stars shine overhead, and their light carries a challenge. They are far, perhaps too far, but they are there. To look at them and say never is to surrender a piece of what makes us human. To look at them and say not yet is to preserve hope. The Alcubierre drive, with its impossible energy demands, has become a symbol of that hope. It whispers that the barrier is not absolute, even if the road to breaching it may take millennia. Still, the barrier is real. The energy requirements are staggering, the materials exotic, beyond imagining. Every refinement softens the problem, but does not erase it. The warp bubble remains perched between the possible and the unattainable. It is a reminder that nature may allow miracles, but demands prices we are not yet ready to pay. The stars remain locked behind equations, and the key, if it exists, lies in a future we cannot yet see. And yet the question does not end here, because energy is not the only price of faster-than-light travel. Even if one could gather the required negative energy, even if civilizations of the far future could harvest dark energy, or manipulate the vacuum itself, another problem rises from the shadows. It is the problem of causality, the fragile thread that connects cause to effect, past to future. Faster than light travel may not only bend space but bend time, opening the door to paradoxes that strike at the coherence of reality itself. If a warp bubble can leap across space faster than light, then under some conditions it may also form loops in time, where a traveler could return before departure. This is the nightmare hidden behind the dream. Thus, as the chapter of energy closes, another begins. The energy barrier may be a mountain, but beyond it lies an abyss, the abyss of causality itself. To master warp is not only to wrestle with power, but to wrestle with time. The next challenge is not simply whether warp is possible, but whether the universe can allow it, without unraveling its own logic. If the Alcubierre drive opened a door, it was not a door only to the stars. It was also a door into time. Faster than light travel does not merely bend distances. It bends cause and effect, the chain of events that forms the backbone of reality. Relativity ties the speed of light to the structure of causality itself. To exceed it is not only to move quickly, it is to risk moving backward. The equations that permit a warp bubble also whisper of loops in time, of journeys that arrive before they depart, of paradoxes that threaten the coherence of the universe. Einstein's theory makes causality sacred. Events are arranged in a web of space-time, where every effect follows a cause. The speed of light is the thread that preserves this order, ensuring that no signal or object can jump ahead of the chain. But when a warp bubble is allowed to move faster than light relative to distant observers, the neat ordering of events can fracture. Under certain conditions, two observers might disagree, not only about the sequence of events, but about which came first. In the warped geometry, it becomes possible to create closed time-like curves, paths through space-time that circle back upon themselves. To travel along such a curve is to travel into one's own past. The consequences are not simply strange, they are catastrophic. Imagine a ship that engages a warp bubble and leaps to a distant star, then returns along a slightly different path. In some reference frames, the return journey might end before the departure began. The crew would step off their vessel into a universe where they had not yet left. The paradoxes spill forth. Could they prevent their younger selves from launching? Could they send warnings that erase the need for the journey? These are not just puzzles of imagination. They are contradictions of logic, fractures in the very foundation of cause and effect. The grandfather paradox is the most famous of these contradictions. Suppose a traveler returns to the past and prevents their own ancestor from surviving. If the ancestor does not survive, the traveler is never born. But if the traveler is never born, they cannot return to the past. The paradox spirals endlessly, unsolvable, within classical logic. Warp bubbles that permit faster than light travel threaten to create such paradoxes, not because they are magical, but because the equations of relativity themselves allow loops when superluminal motion is introduced. The structure of space-time folds back upon itself, and the arrow of time loses direction. Physicists have wrestled with this possibility for decades. Some suggest that the universe has built-in safeguards, laws that forbid the creation of closed, time-like curves. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics prevent time travel on macroscopic scales. According to this conjecture, any attempt to form a warp bubble or wormhole that could create paradoxes would collapse under quantum effects, exploding in radiation or destabilizing before a loop could form. In this way, the universe would protect its own consistency, sacrificing warp bubbles if necessary, to preserve causality. But conjecture is not proof. No one yet knows whether chronology protection is absolute. Quantum gravity, the missing union of relativity and quantum mechanics, may hold the answer. Until that theory is complete, the paradoxes remain unresolved. The equations permit closed time-like curves, yet the logic of reality recoils from them. We stand in the tension between mathematics and meaning, between what equations allow and what existence can sustain. For those who dream of warp, the threat of causality violation is perhaps more daunting than the energy barrier. Energy requirements, at least in principle, can be imagined away by invoking future civilizations with godlike power, but paradox cannot be engineered around. If the laws of logic forbid closed loops, then the warp drive may collapse not under lack of fuel, but under contradiction itself. To master space-time may not only require infinite energy, it may require rewriting the rules of time. When physicists contemplate faster than light travel, they often speak not only of propulsion, but of paradox. The two are inseparable. To move faster than light is to outrun the very signal that defines order in the universe. It is to allow information to arrive before it is sent, to blur the arrow of time. The mind resists such an idea, but the equations embrace it, yielding scenarios that border on the surreal. One of the simplest thought experiments involves two ships equipped with warp drives. Suppose the first leaps to a distant star and sends a signal back by conventional light speed means to an observer on Earth. The signal might arrive long after the ship has departed, but to another observer, moving at a different velocity relative to the first, the order of events can appear reversed. With carefully arranged journeys, the paradox sharpens. One ship departs, another arrives, and in some frames of reference the arrival precedes the departure. What was cause becomes effect, and what was effect becomes cause. The threads of time knot themselves into loops. Closed time-like curves are the mathematical embodiment of this nightmare. They are not science fiction metaphors, but solutions to Einstein's equations. In such curves, a traveler following the laws of relativity can move forward in proper time while circling back to the same point in space-time, effectively returning to the past. Wormholes are known to permit such curves under certain conditions. Warp bubbles, if allowed to exceed light speed, risk creating them as well. The universe, so elegantly ordered under subliminal motion, becomes a hall of mirrors when superluminal paths are introduced. The implications are staggering. If time travel to the past is possible, then history is not fixed. Every moment could be vulnerable to alteration, but alteration implies contradiction. If a traveler prevents a disaster, then the motivation to travel back vanishes, erasing the prevention. If a message warns of an accident, then the accident never happens, negating the need for the warning. The loops collapse under their own logical weight. Nature, we assume, does not permit contradictions, yet relativity alone, without further restrictions, does not forbid them. How then can these contradictions be resolved? Some physicists invoke the multiverse. In this view, traveling back in time does not change one's own past, but creates or enters an alternate branch of reality. The traveler kills their ancestor in one branch, but in their original branch, they still exist. The paradox dissolves, replaced by a branching tree of universes, where every possibility is realized. This interpretation is speculative, but it aligns with certain readings of quantum mechanics, where probabilities unfold across many worlds. If the multiverse is real, warp-driven time travel may not break logic but multiply it, spawning endless variations of history. Others prefer Hawking's chronology protection idea, believing that paradoxes themselves are evidence that nature intervenes. Perhaps quantum effects generate violent bursts of radiation whenever closed time-like curves begin to form, destroying the would-be time machine. Perhaps the very conditions required to sustain a warp bubble collapse before paradox can arise. In this view, the universe defends its coherence as fiercely as it defends the speed of light, closing loopholes before they become disasters. We may imagine bubbles of space-time flickering into instability, annihilating themselves in bursts of quantum fire the instant they threaten causality. Still, others suggest that paradoxes might be avoided by consistency conditions. According to this idea, any journey into the past would always be self-consistent. A traveler could visit history but never change it in a way that contradicts their own existence. The universe in this model, enforces consistency by subtle adjustments. The traveler may try to prevent an event, but fail in unforeseen ways, ensuring that the timeline remains intact. This is known as the Novikov self-consistency principle. It preserves logic, but at the cost of freedom, binding all actions to a single, unalterable chain of cause and effect. Each resolution carries its own philosophical weight. The multiverse dissolves paradox but multiplies reality. Chronology protection preserves logic by forbidding the dangerous geometries. Consistency principles preserve timelines, but strip choice from travelers. None are proven, for all depend on physics beyond our current reach. What they reveal is not certainty, but the depth of the problem. Faster than light travel, by its very nature, drags causality into question. To solve the energy problem is not enough. To master warp, we must also master time. Causality is the silent foundation of the universe. It is the thread that ties every event to the one before it, the rhythm that makes time meaningful. We scarcely notice it because it never breaks. We wake after sleeping because yesterday happened. We drop a stone, and it falls because gravity acts in sequence. We send a message and expect it to arrive after we send it, not before. To tamper with faster than light travel is to tamper with this foundation, and the dangers are more profound than any question of fuel or engineering. Stephen Hawking warned of this with unusual directness. His chronology protection conjecture was not merely technical but philosophical. He suggested that the universe has an instinct to preserve its own coherence. Just as the speed of light prevents the violation of relativity, so too quantum effects might prevent the violation of causality. Whenever a geometry threatens to form a closed loop in time, virtual particles could swell into storms of radiation, collapsing the structure before paradox is born. In this way, nature itself guards its timeline, refusing to permit the contradictions that logic cannot tolerate. But Hawking's conjecture, however elegant, remains unproven. No experiment has yet touched these realms. We cannot test warp bubbles in laboratories, nor can we stabilize wormholes to watch them collapse. All we have are equations, partial hints from quantum field theory, and the insistence of reason that contradictions must not exist. Yet nature does not always obey human reason. It often surprises us, stretching the boundaries of what we thought possible. We must therefore leave open the question, even as we fear its implications. If warp bubbles could be built, and if they could travel faster than light without collapsing, then paradoxes might be unavoidable. Perhaps the solution is multiversal branching, where every contradiction is dissolved into new timelines. Perhaps the solution is consistency, where every attempt to alter history only fulfills it. Or perhaps there is no solution, and the very attempt would tear space-time apart. Each possibility is staggering, for each redefines what it means to exist in time. The stakes extend beyond physics. To touch causality is to touch meaning. If history can be rewritten, then identity itself trembles. Who are we, if our past can be undone? What is memory, if the future can erase it? These are not only philosophical questions, but existential ones, bound to the physics of time as tightly as to the flow of thought. Warp speed, by threatening to outrun light, threatens also to outrun logic, to turn the straight arrow of time into a circle, with no beginning and no end. And yet, the dream persists. We look at the stars and imagine ships leaping across the void. We imagine families settling distant worlds, explorers charting the spiral arms of the galaxy. We imagine contact with civilizations light years away, made possible by journeys faster than light. In every vision, the paradoxes are quietly ignored. Fiction whispers of possibility without pausing to confront contradiction. But science cannot afford such silence. It must confront the question directly. If warp drives can exist, then can the universe remain whole? This is the threshold where energy and causality meet. Energy demands more than galaxies. Causality demands more than consistency. To conquer both is to ask whether the universe itself will allow the attempt Perhaps the laws of physics are arranged not only to preserve order, but to preserve story, to prevent the unraveling of the chain that gives reality coherence. If so, then faster-than-light travel is more than difficult. It is forbidden in the deepest sense. But if not, if the universe allows loopholes, then warp speed could open not only the stars, but the corridors of time. As this chapter closes, we stand at the edge of that terrifying thought. Warp speed is not only a question of motion, it is a question of existence. If the energy problem could somehow be solved, if negative energy could be mastered, we would face the greater challenge, whether traveling faster than light unravels the very fabric of cause and effect. The next step is to distinguish light itself from warp, to understand why one is bound and the other may slip free, and to see whether the difference holds the key to preserving reality. For all the discussion of faster-than-light travel, there is a danger of blurring two very different things. Light speed is a limit on motion through spacetime. Warp speed is an attempt to reshape spacetime itself. To confuse them is to miss the subtlety of Einstein's vision and the daring of Alcubierre's proposal. They are not the same, and understanding the difference is essential before we can even imagine what it would mean to ride a warp bubble through the stars. Light moves at 299,792 kilometers per second in a vacuum. This number is not only the velocity of photons, it is the velocity that defines the relationship between space and time. The structure of relativity is built around it. No signal, no particle, no ship can move faster through space-time without demanding infinite energy. This is the cosmic speed limit, woven into the fabric of geometry itself. The constancy of light speed is why time dilates, why lengths contract, why mass seems to grow as objects accelerate. It is the keystone of causality. Warp speed, as Alcubierre described, is something altogether different. In a warp bubble, the ship itself does not move faster than light relative to its local space. Inside the bubble, the crew drift as though motionless. Their clocks tick normally. Their bodies feel nothing unusual. What moves is the bubble itself, carried by the expansion and contraction of space-time. Space ahead contracts, drawing the destination nearer. Space behind expands, pushing the origin farther away. To an external observer, the bubble can appear to leap faster than light. But in strict terms, no local law is broken. Light still outruns everything inside its patch of space-time. It is space-time itself that has been bent to cheat the limit. The distinction is subtle but vital. Imagine standing on a shoreline watching waves roll past. A surfer on the crest of one wave seems to move far faster than the flow of water beneath him. The water molecules do not rush across the ocean. They oscillate in place, rising and falling as the wave passes. The surfer's speed is the speed of the wave, not the water. In the same way, a ship in a warp bubble is not outrunning photons in its local frame. It is riding a wave of curvature, carried along as space-time itself shifts. From the perspective of distant observers, the ship appears to break the light barrier, but from its own perspective, nothing of the sort has happened. This difference explains why warp does not violate relativity, even though it seems to. Relativity forbids motion faster than light through space-time, but it does not forbid space-time itself from evolving in ways that mimic faster than light travel. The expansion of the universe already demonstrates this. Distant galaxies recede from us faster than light because the space between us grows. Yet the galaxies themselves are not breaking the limit. They are stationary in their local frames, carried by the flow of expansion. Warp speed is an attempt to localize that cosmic phenomenon, to bottle the expansion and contraction into a controlled bubble around a ship. But what would this look like? To imagine warp speed is to imagine a different relationship with the universe. Light is absolute, a ruler by which all motion is measured. Warp is relative, a sculpting of the ruler itself. The ship, inside the bubble, would not see itself racing through stars, as in fiction. Instead, The stars would distort as space-time bent around them. Ahead, light would be squeezed into blue shift, compressed into higher energies as the bubble contracted space. Behind, light would be stretched into redshift, elongated into lower energies as the bubble expanded space. The view would be alien, a shifting lens of warped starlight painting the cosmos in hues beyond human eyes. The crucial point is that warp does not erase the light barrier. It sidesteps it. It is not about breaking through a wall, but about moving the wall itself. The ship inside the bubble obeys relativity completely. It never accelerates beyond what physics allows. It simply occupies a region of space-time that has been shaped to carry it where it wishes to go. The metaphor is not of running faster, but of folding the track. A runner limited by speed cannot beat the record by sprinting harder. But if the track itself is bent, so the finish line lies closer, the race is won, without breaking the rule. Warp is the bending of the track of space-time. This is the distinction that makes warp both alluring and unnerving. It seems to offer freedom while still respecting the laws of physics, but it does so by invoking powers of geometry that are far beyond current control. Light is straightforward, a speed we can measure and test. Warp is abstract, a manipulation of the very fabric of existence. To imagine controlling it is to imagine playing with the scaffolding of the universe, the grid upon which all motion, all time, all causality rests. It is both more possible and more dangerous than the naive dream of simply outrunning light. To grasp the strangeness of warp, we must linger on what light itself represents. Light is not merely illumination, it is the heartbeat of space-time. Every second of our lives is measured against its rhythm. When a photon leaves a star and crosses the galaxy, it does not experience time as we do. In its own frame, no time passes at all. The journey of thousands or millions of years collapses into an instant. For us, trapped below the limit, light is impossibly fast. For light itself, there is no journey, only presence. This duality is what makes the speed of light so absolute. It is not just a velocity, it is the structure of reality. Now imagine a warp bubble. Inside, the ship and its crew are bound by relativity, as usual. They cannot match light, let alone exceed it. Their clocks tick steadily. Their bodies remain anchored in ordinary time. But outside, the bubble's wavefront reshapes the geometry. From a distant perspective, the bubble might appear to leap across light years in a fraction of the time. The paradox is only apparent. Nothing inside the bubble outruns photons in its local space. Instead, photons themselves are caught in the distortion, bent and twisted, as space-time reshapes itself around the vessel. This is why warp feels so alien compared with conventional speed. Speed is intuitive. It is motion relative to distance and time. Warp is not motion at all. It is geometry, redefined. A ship at warp is not rushing through the galaxy. The galaxy itself is being folded, compressed in front, and stretched behind. The destination arrives not because the ship covered the distance, but because the distance itself changed. It is not acceleration, but transformation. The visual consequences of this transformation are extraordinary. Ahead of the bubble, space is squeezed, and with it, light waves compress. To the crew, the starlight forward would shift towards shorter wavelengths, a cosmic blue shift that could push visible light into ultraviolet or even higher energies. Behind the bubble, the opposite occurs. Light stretches into longer wavelengths, bleeding into red and infrared, perhaps radio. The sky would distort into a surreal panorama, a cone of blinding brilliance ahead, a fading trail of stretched darkness behind. Fiction often shows stars streaking past as lines, but reality would be stranger, a warped funnel of light, compressed and stretched by the bubble's relentless sculpting. For an outside observer, the effects are equally dramatic. The bubble itself is not invisible. Its boundaries would distort the passage of light, lensing the background in peculiar ways. Just as massive galaxies bend the light of more distant galaxies, creating arcs and rings in the sky, so too would the warp bubble bend starlight around it. To telescopes, it might appear as a shimmering lens, racing faster than light, dragging distorted images of the cosmos in its wake. The ship inside would be hidden from view, cloaked in the curvature that carries it. Warp would not be a clean leap, but a visible wound in space-time, a ripple across the fabric of the universe. And yet, despite this spectacle, relativity remains unbroken. The crew inside feel nothing unusual. Their ship experiences no acceleration. Their instruments measure no violation of light speed locally. Everything remains consistent in their frame. It is only in the comparison of frames, in the relationship between inside and outside, that the illusion of faster than light emerges. Warp is not a sprint, but a sleight of hand, a redefinition of the board upon which the pieces move. This difference between light and warp is not merely academic. It is the reason physicists take Alcubierre's solution seriously. If he had proposed that a ship could simply accelerate past light speed, the idea would have been dismissed as nonsense. But by anchoring the concept in space-time curvature, Alcubierre preserved relativity. He offered not rebellion against physics, but obedience in disguise, twisting the rules without breaking them. The warp bubble became credible not because it ignored Einstein, but because it embraced him fully. The contrast can be drawn like this. Light speed is an absolute wall for motion within space-time, while warp speed is an attempt to move the wall itself. Light is the ceiling of the room. Warp imagines shifting the entire room so that the ceiling remains intact, even as the occupant seems to move beyond it. The physics of photons remains untouched, but the context in which photons exist has been rearranged. This rearrangement raises questions beyond physics. What does it mean for distance to lose meaning? If warp collapses the gap between stars, then the size of the galaxy itself becomes malleable. The cosmos, once defined by its immensity, could become as navigable as seas once were. But this navigability is not speed in any ordinary sense. It is mastery over the stage itself, the bending of reality's geometry to human will. The distinction between light and warp is the distinction between running across a field and folding the field so that the finish line touches your feet. The difference between light and warp is more than a technicality. It is a difference in how the universe itself is experienced. Light speed is the ultimate rhythm of reality. Every process in the cosmos, from the flicker of atoms to the birth of galaxies, is chained to it. Warp is an intrusion into that rhythm, not by breaking it, but by reshaping the stage on which it plays. To cross the stars by warp would not be to travel in the human sense. It would be to command the very distances themselves to change, to order the map of the cosmos, to redraw itself around you. What would this feel like? Inside the bubble, perhaps nothing at all. The crew would sit in quiet stillness, instruments steady, clocks ticking normally. The stars outside would twist and distort, but the ship itself would float in serene free fall. Unlike rockets, there would be no vibration, no thrust, no sensation of motion. Warp would be silent, invisible to those within, a voyage without travel. The paradox is that the most extraordinary journey imaginable would feel like nothing at all. Yet the view through the windows, if windows could exist in such a geometry, would tell a different story. Ahead, the sky would blaze with compressed starlight, a funnel of brilliance as photons squeezed into shorter wavelengths. Behind, the sky would fade into stretched darkness, light elongated into whispers of radio. The stars would no longer seem scattered across a dome, but bent into arcs and halos, distorted by the curvature of the bubble. To sail at warp would be to look into a sky no human eye has ever seen, a sky sculpted by the bending of reality itself. The philosophical meaning is just as profound. Light speed defines equality. No observer can outrun it. No frame can claim it moves faster or slower. Warp threatens to fracture that equality by creating bubbles that appear to leap ahead of the universal limit. But the threat is only apparent. In truth, warp preserves the local constancy of light, while altering the global arrangement of space. It is not rebellion, but exploitation. Not law-breaking, but law-bending. This is why warp fascinates scientists and dreamers alike. It sits at the razor edge between impossibility and inevitability, a loophole carved from the very rules that seemed unbreakable. In the end, light is the cosmic law, warp the human challenge. Light is the heartbeat of space-time, warp the attempt to rewrite the melody. Light is universal, indifferent, absolute. Warp is selective, deliberate, intentional. To master warp would be to move beyond speed into something stranger, a realm where distance itself is a tool to be shaped. This is the essence of the difference. Light is the universe as its island. Warp is the universe, as we might someday dare to remake it. As this chapter closes, one question lingers. If warp is not motion but geometry, not speed but sculpting, then what dangers might lurk in such a manipulation? To fold space is not like steering a ship. It is like steering the fabric of existence itself. What happens when distortions build? What accumulates at the front of the bubble? What energy waits to be released when the bubble collapses? These are the hazards of warp, the shadows that follow the dream, and they demand attention before the fantasy can feel safe. Every dream has its shadow, and warp is no exception. To bend space-time is not like bending a sheet of paper. It is to reshape the very medium through which light and matter move. The equations that allow the warp bubble also predict that it carries dangers, some subtle, some catastrophic. Fiction shows starships leaping to warp as though engaging a switch, smooth, silent, and effortless. Reality, if it ever permits such voyages, may be far harsher. The hazards of warp are not inconveniences. They are existential. The first danger arises from light itself. As the bubble contracts space ahead, photons are caught in the distortion. Starlight, cosmic radiation, stray particles, all are dragged forward and squeezed. With every moment the bubble travels, more energy accumulates at its prow. Like snow piling before a plow, the bubble sweeps radiation into an ever denser wall. To the crew inside, this may go unnoticed, for the bubble's interior is shielded by its geometry. But the wall outside grows, a tide of compressed energy, waiting to be released. Physicists who analyzed this effect reached unsettling conclusions. When the bubble decelerates, when the distortion collapses, the accumulated energy must go somewhere. It would burst outward in a torrent of radiation, a blast potentially lethal to any planet or ship in its path. A single warp journey might end with the release of enough energy to sterilize a world. The starship would arrive at its destination, not as an ambassador, but as a weapon, its very motion transformed into devastation. This hazard alone casts a dark shadow on the dream of interstellar travel by warp. Particles, too, accumulate at the bubble's front. Interstellar space is not empty. It holds dust, gas, stray atoms drifting between the stars. At subluminal speeds, spacecraft pass through this medium with little concern. But at warp, the contracted space ahead sweeps these particles into the distortion. They too pile up, compressed into lethal concentrations. When the bubble collapses, the release would be catastrophic, like detonating a cosmic minefield. Warp travel, in this sense, is not only dangerous to the destination but also to the traveler, who risks annihilation by the very fabric of the medium they sought to cross. Another hazard lies in stability. The warp bubble is not a rigid shell, but a fragile geometry, a balance of expansion and contraction. Small perturbations may disrupt it, causing the bubble to collapse prematurely. If that collapse occurs while traveling faster than light relative to distant observers, the result could be catastrophic, hurling the ship into destructive forces or shredding it in tidal distortions. Maintaining stability may require exquisite control over negative energy distributions, adjustments at scales finer than any technology we possess. A warp drive may not fail gracefully. It may fail violently. And then there is the problem of control. From inside the bubble, the crew cannot send signals to the bubble's front, because locally, they never outrun light. This means they cannot steer or navigate the bubble once it is in motion. The ship would be carried like a passenger in a runaway current, unable to communicate with the leading edge that shapes its path. How then does one stop? How does one aim? To ride a warp bubble is to surrender control, trusting that the geometry unfolds as planned. Any deviation might strand the travelers light years from their destination, or worse, plunge them into hazards unseen. These dangers are not afterthoughts. They are inherent in the very mathematics of the warp bubble. Energy accumulates because of how space-time bends. Instability arises because of how delicate the geometry must be. Lack of control follows from the fact that causality inside the bubble is disconnected from causality outside. Each hazard is a natural consequence of the mechanism itself, not a flaw of engineering, but a warning inscribed into the equations. To ignore them is to mistake dream for destiny, and yet the dream endures. Even knowing the hazards, physicists explore the warp bubble as a thought experiment. Perhaps refinements can reduce the accumulation of radiation, dispersing it gradually rather than catastrophically. Perhaps new geometries can stabilize the bubble or allow limited control from within. Perhaps future theories of quantum gravity will reveal mechanisms that tame these dangers. But for now, the hazards remain towering, as formidable as the energy barriers and as forbidding as the paradoxes of causality. Warp is not only a challenge of creation, it is a challenge of survival. The notion that a starship might arrive from warp and unleash devastation is not merely a detail hidden in calculations. It is a fundamental flaw. Every bubble that compresses space ahead is gathering photons and particles into a growing wall. Imagine centuries of starlight, cosmic rays, and drifting atoms, all funneled into an infinitesimal region. The energy stored in that wall could dwarf the largest nuclear arsenals ever conceived. When the bubble collapses, the release would not be subtle. It would be a burst of high-energy radiation, capable of scorching planets, vaporizing atmospheres, and sterilizing biospheres. Warp, in this sense, risks becoming indistinguishable from a weapon of planetary annihilation. Some theorists have suggested that the energy might dissipate gradually if the bubble is slowed carefully. But the mathematics offers little comfort. The accumulation is a structural feature of the bubble's distortion. Slowing down may not bleed away the energy, but simply delay the inevitable. Even a carefully managed deceleration could unleash a beam of radiation powerful enough to destroy everything in its path. The ship itself might be obliterated in the very moment of arrival, consumed by the release it triggered. The dream of leaping between stars begins to look less like exploration and more like suicide. Instability is another peril. A warp bubble is not a solid shell, but a dynamic field of curvature, a delicate balance between contraction ahead and expansion behind. To maintain that balance may require precision beyond imagining. A fluctuation in negative energy density, a quantum jitter in the vacuum, could destabilize the bubble. Collapse might scatter the ship across distorted space-time, tearing it apart molecule by molecule, or it might eject the ship violently, spitting it into normal space at relativistic velocity, with no protection against the lethal impact of interstellar dust. The risks are not minor. They are existential, inherent in the fragile structure itself. Control, too, becomes almost impossible. Inside the bubble, light cannot travel forward faster than the bubble's leading edge. This means no signal, no command, can reach the front to adjust course. The crew cannot steer around hazards, because by definition, they cannot communicate with the space that defines the bubble's path. Navigation must be set in advance, a trajectory locked before departure. Once in motion, the ship is a passenger of its own distortion, helpless until the bubble collapses. In practical terms, warp is not a voyage, but a blind leap, one that may end light years from the intended target or in the heart of a star. Even communication becomes a nightmare. From inside the bubble, signals cannot escape forward. To an outside observer, the ship vanishes into silence, its messages trapped by the geometry that carries it. Only when the bubble collapses can communication resume, long after the ship has arrived if it survives the release. In a universe where navigation and coordination are essential, this silence is not just inconvenient, it is crippling. Civilizations that attempt warp may find themselves isolated with every journey, cut off until the dangerous leap ends. The hazards extend beyond the travelers. Consider a civilization that masters warp. Every journey risks releasing bursts of radiation at the destination. Even a single miscalculation could obliterate a colony world or sterilize a system. Interstellar travel would become inseparable from interstellar warfare. Every ship, a potential bomb, whether intended or not. The galaxy could never be safe. Warp drives would be weapons by their very nature, not by design, but by consequence. The dream of exploration could become a nightmare of destruction. And yet, the hazards remain speculative. The equations predict them, but no bubble has ever been created to test them. Perhaps refinements exist that dissipate the energy safely, or geometries that permit steering and communication. Perhaps quantum effects smooth out instabilities before they can destroy the ship. But until such mechanisms are found, the hazards stand like warnings on the edge of possibility. They remind us that bending space-time is not like bending tools. It is bending the canvas on which reality itself is painted, and the canvas resists. These dangers do not erase the dream, but they reshape it. Warp is no longer simply a path to the stars. It is a path fraught with risk, demanding solutions as radical as the concept itself. If energy barriers mock us with impossibility, hazards mock us with danger. Between the two lies a narrow corridor where hope resides. But hope alone cannot carry a ship across the galaxy. It must face the shadows, or the dream will consume itself. Warp's dangers remind us of a truth often forgotten in the glow of speculation. The universe is not gentle. It resists shortcuts with ferocity. Radiation, instability, and loss of control are not engineering glitches waiting for clever fixes. They are consequences written into the equations themselves, warnings carved in the fabric of geometry. To imagine warp is to imagine not only freedom, but peril. A ship may cross light years in an instant, but it may also arrive shrouded in fire. Its very arrival, an act of destruction. The same distortion that carries life across the stars could just as easily extinguish it. There is an irony here. The very mechanism that preserves relativity within the bubble creates catastrophe outside it. The crew inside experience serenity, drifting as though in stillness. The outside, however, pays the price. Photons pile at the prow, particles crush together, radiation builds, and stability falters. The bubble protects those within, while imperiling everything without. It is a paradox of safety and danger, sanctuary and threat. A civilization that used warp indiscriminately would find itself a hazard to its own expansion, scattering destruction with each arrival. The dream of peaceful exploration could curdle into fear of warp itself, a technology too dangerous to unleash. Some argue that this may be the hidden reason why we have not encountered alien civilizations. If warp travel truly carries such risks, then perhaps no species has ever mastered it safely. Or perhaps those who did were undone by the very hazards that accompanied it. Their colonies burned by the unintended blasts of arrival, their fleets destroyed by instabilities in space-time. In this view, warp may be less a doorway to the stars and more a filter, a challenge so lethal that no civilization survives its attempt. And yet, humanity has never been deterred by risk. We have hurled ourselves into oceans without maps, flown fragile machines into hostile skies, and split atoms despite the fire within them. The hazards of warp may be monstrous, but so were the storms that swallowed early sailors. So were the flames that consumed early aircraft. Dangers do not extinguish dreams. they sharpen them, reminding us that progress is never free. The cost of warp, if it can be paid at all, may be vigilance, restraint, and ingenuity beyond imagination. Philosophically, warp's hazards force us to confront responsibility on a cosmic scale. To bend space-time is to wield forces that could devastate worlds. No society could use such power without grappling with ethics as well as physics. To risk annihilation with every voyage is to stand at the edge of cosmic recklessness. Perhaps warp is not meant for conquest or colonization, but only for those who can carry it with wisdom. In that sense, the hazards are not only physical but moral, a test of whether a species deserves to command the fabric of reality. As this chapter closes, the dream of warp has grown darker. The stars remain tempting, but the path to them is strewn with dangers more fearsome than distance itself. Energy barriers threaten impossibility. Hazards threaten annihilation. Together they form a gauntlet, daring any who dream of the stars to attempt the passage. Some will see in this a warning to abandon the dream. Others will see a challenge to rise higher. Yet amid the dangers, one truth remains. Space-time is malleable. It bends and curves under gravity. It stretches under expansion. It folds in the presence of mass. Nature itself already sculpts the cosmos in ways warp seeks to imitate. Black holes twist space into funnels. Wormholes, at least in theory, connect distant regions. Gravity is the original warp drive, the hand that shows us what curvature can achieve. Perhaps by studying gravity more deeply, by learning from nature's own experiments, we may discover whether warp is folly or destiny. If warp seems like a dream of science fiction, gravity reminds us that space-time already bends. Every star, every planet, every black hole is proof that the fabric of the cosmos is not rigid but pliable. Mass and energy curve space. That curvature guides the paths of light and matter, shaping orbits, bending starlight, and holding galaxies together. Warp is not the invention of human imagination. It is an echo of what nature already does with ease. The difference is that nature bends space-time with the weight of suns, while humanity dreams of bending it with machines. Einstein revealed this truth in 1915 when he published the General Theory of Relativity. According to his equations, gravity is not a force in the traditional sense, but the result of curved geometry. A planet does not orbit the sun because of an invisible pull. It follows a path, a geodesic, through the curved space-time sculpted by the sun's mass. The apple does not fall from the tree because Earth tugs on it, but because space-time itself guides it downward. In this picture, space-time is a stage that responds to every actor upon it, reshaping itself to match the distribution of energy and mass. Warp attempts to imitate this. Where a star warps space with mass, a warp drive would warp it with engineered fields of expansion and contraction. The mathematics is similar, a region of curvature guiding a vessel's path, but there is a difference in intention. Gravity shapes space unconsciously, the passive outcome of mass existing. Warp would shape space deliberately, the active manipulation of geometry. Nature bends space-time without effort. Humanity would attempt to bend it by will. Black holes are the most extreme demonstration of gravity's power. They curve space so sharply that not even light can escape. Around their edges, starlight bends into arcs and rings. Matter spirals at near light speed, and time itself slows for outside observers. In these regions, gravity becomes warp-like, dragging space-time around with it. The phenomenon known as frame dragging, predicted by relativity and confirmed by satellite experiments, shows how rotating masses twist space-time like a spoon stirring water. In a sense, every spinning planet, every star, every black hole is already a primitive warp drive, moving space-time around with its rotation. Wormholes extend this idea further. Solutions to Einstein's equations suggest that space-time can form tunnels connecting distant regions. A wormhole is not faster than light travel in the ordinary sense. It is a shortcut. Instead of crossing the galaxy, one steps through a bridge that links two points. To an outside observer, the traveler seems to leap across impossible distances in no time at all. To the traveler, the journey is simply walking through a corridor. Wormholes, like warp bubbles, require exotic conditions to remain stable, often invoking negative energy to keep their throats open. In this way, wormholes and warp are siblings. One folds space into a bubble that carries a ship, the other folds space into a tunnel that bypasses distance. The connection between gravity and warp is profound. Warp is not an alien idea bolted onto relativity. It is relativity's own flexibility, pushed to its extreme. Einstein's equations do not forbid such geometries. They invite them. They whisper that space-time is malleable, that distances are not sacred, that the fabric can be folded in ways we barely comprehend. Gravity is the natural demonstration of this truth, a reminder that space-time responds to energy. Warp is the dream of taking that response into our hands. Yet the comparison also reveals a humbling truth. Gravity bends space-time with mass far greater than any we can command. A star curves the space around it without effort, holding planets for billions of years. A black hole warps the cosmos into singular funnels of infinity. Compared to this, the energies proposed for warp bubbles seem both familiar and impossible. We understand the principle because we see it in nature. We despair of the scale because nature wields powers we cannot match. Warp, then, is gravity's shadow, a mirror of what already exists, but beyond human reach. If warp bubbles represent humanity's attempt to sculpt space-time into motion, wormholes are nature's own blueprint for shortcuts. The mathematics of general relativity admits the possibility of tunnels through space-time, passages that connect distant points as though the cosmos were folded and stitched together. The image is almost mythic, a hidden door in the vastness of the universe, but it arises directly from Einstein's equations. Wormholes are not science fiction inventions. They are legitimate solutions, even if no one has ever seen one. The idea began in the early 20th century, when Einstein and Nathan Rosen examined the geometry of black holes. They discovered that the equations describing a black hole also permitted a bridge connecting two regions of spacetime. This became known as the Einstein-Rosen bridge. At first, it seemed a curiosity, for the bridge was unstable and would collapse too quickly for anything to pass through. Later work showed that exotic matter again, negative energy density, could in principle stabilize such a throat, keeping it open long enough for travel. Here, the parallel with Alcubierre's bubble is striking. Both warp drives and wormholes require forms of energy alien to our experience. Both are mathematically allowed, but physically elusive. Wormholes are different from warp in how they cheat distance. Warp drags a bubble across space, contracting and expanding regions to move a vessel. Wormholes fold space into a tunnel so that the traveler steps through instead of around. One is a wave, the other a door, but both rest on the same foundation. Space-time is flexible, and geometry can be manipulated. Each represents a way of slipping past the tyranny of light speed without directly breaking it. Each demonstrates how relativity, far from forbidding imagination, expands it. The similarities extend further. Wormholes, like warp bubbles, create potential paradoxes. A traversable wormhole, if moved or accelerated, can generate closed time-like curves, allowing travel into the past. The same hazards of causality that haunt warp also haunt wormholes. Chronology protection may slam the door on both, ensuring that no such tunnels can be made stable. In this way, wormholes and warp are twins not only in possibility, but in peril. Both open the stars, both threaten time. For a civilization seeking to cross interstellar gulfs, wormholes might seem more efficient than warp. A stable wormhole, once built, could remain open indefinitely, serving as a permanent bridge. Travel through it would take no time at all, regardless of distance. Colonies could be linked like neighboring towns, no matter how many light years apart. Warp bubbles, by contrast, require fresh energy for each journey, fragile and temporary distortions that collapse at the end of the trip. Yet wormholes may be even harder to create than warp bubbles. They demand not only negative energy, but also a mastery of geometry on cosmic scales, sculpting space-time into structures far larger and stranger than anything imagined in engineering. Still, wormholes reveal that the dream of faster-than-light travel is not an aberration. It is an echo of possibilities already written into the universe. General relativity, in its relentless logic, permits not only orbits and expansions, but shortcuts and distortions. The universe is not a rigid grid, but a malleable fabric, one that nature already bends with gravity, and that equations suggest could be bent in stranger ways. Still, warp and wormholes are not intrusions into this framework. They are its natural extremes. The boundary between science and science fiction blurs here. When fiction shows ships vanishing into tunnels or streaking across bent space, it draws not from fantasy, but from mathematics. The challenge is not whether the ideas are consistent with relativity. They are. The challenge is whether the universe permits them to be realized beyond equations. This is the great uncertainty that hovers over both warp and wormholes. They are allowed, but are they possible? They are written in the language of space-time. But will nature ever allow us to speak that language in practice? The parallel reminds us that warp is not an isolated curiosity. It belongs to a family of solutions that reveal the plasticity of space-time. Wormholes, black holes, cosmic expansion, all show that distances and times are not absolute. They can stretch, twist, and connect in ways far removed from everyday intuition. Gravity is the silent sculptor, bending space-time in patterns we can measure but not yet command. Warp and wormholes are humanity's attempt to take up that chisel, to carve the fabric of reality with intent rather than with mass. The tools are not yet in our hands, but the designs are already inscribed in the equations. Gravity shows us that space-time is not fixed. Every orbit, every lens of starlight around a galaxy, every black hole that swallows time itself is proof that the fabric of reality bends. Warp and wormholes are not fantasies imposed upon this fabric, but reflections of what it already does. The difference is that gravity bends space with mass and energy as they naturally exist, while warp demands that we bend it deliberately, with forces far beyond our present reach. The two are rivals only in ambition. In truth, they are partners, for warp is nothing more than an attempt to borrow gravity's tools and wield them with intent. Black holes in particular remind us how close warp lies to nature's own extremes. Around a rotating black hole, space itself is dragged along with the spin. This frame dragging is so powerful that nothing can resist. Even light is twisted by the swirl, forced to follow the vortex of space-time. This is not metaphor. Satellites orbiting Earth have measured the effect on a tiny scale, confirming Einstein's predictions. If a planet as small as Earth can stir space-time faintly, a black hole stirs it ferociously, sculpting geometry as though it were liquid. In this sense, gravity is the original warp drive, shaping reality, not by intention, but by existence. To study gravity is therefore to study warp in its natural form. Every gravitational lens, where a galaxy bends light from another galaxy into arcs, is a demonstration of geometry as transportation. The light takes a shortcut not because it moves faster than light, but because space-time itself curves. Every orbit of a planet is a journey guided by curved paths. Every expansion of the cosmos is space itself carrying galaxies apart. The dream of warp is to take these natural lessons and compress them into a bubble, to imitate the cosmos with machinery. The line between natural and artificial is thin, for both obey the same equations. This recognition changes how we view the dream. Warp is not alien to physics, it is physics. It is gravity by another name, geometry made portable. The challenge is not to invent it, but to control it, to compress into a ship what the universe expresses in stars and black holes. If we could ever master negative energy, If we could shape space-time with precision, warp would not be a violation, but a continuation of nature's own artistry. But this is where humility returns. The cosmos bends space with masses so great they collapse into singularities. Humanity bends space only faintly, measuring minuscule curvatures from planets and moons. The scale is staggering, the gulf between what nature achieves and what we can imagine. To think of building a warp drive is to think of holding the power of suns in human hands. It is both awe-inspiring and sobering, a reminder that the tools we dream of are already wielded by the cosmos in ways we barely understand. As this chapter closes, warp and gravity stand revealed not as enemies, but as mirrors. Gravity is the natural warp drive, the proof that space-time yields to mass and energy. Warp is humanity's attempt to turn that proof into practice, to transform passive curvature into deliberate travel. Between them lies the question of possibility. Can we ever command the forces that gravity wields so effortlessly? Or will warp remain only a dream, a reflection of powers that belong to stars alone? The answer belongs to the future. And so the story turns again, from nature's examples to humanity's ambition. What lies ahead for the dream of faster than light travel? Are NASA and theoretical physicists discovering hints of paths forward? Could dark energy or quantum gravity unlock the door? Or will warp remain a symbol forever beyond reach? These questions guide us into the next chapter, where the future of faster-than-light dreams is weighed against the stubborn laws of the universe. The idea of warp could have remained a curiosity in the pages of journals, a mathematical sketch admired for its elegance and dismissed for its impracticality. But something about Alcubierre's solution refused to fade. Perhaps it was the resonance with fiction, or perhaps it was the sheer audacity of bending space-time as casually as sailors bend sails. Whatever the reason, the warp drive did not vanish into obscurity. It captured imaginations across the world, including those of engineers and scientists at NASA. For the first time, a government space agency began to discuss warp not only as fantasy but as a speculative line of research. In the early years of the 21st century, a small team at NASA's Johnson Space Center, led by Harold White, began to explore refinements to Alcubierre's equations. Their goal was not to build a warp drive, no such thing was possible with existing technology, but to test whether the energy requirements might be reduced by clever geometries. White proposed that by shaping the warp bubble into a ring rather than a sphere, the demand for negative energy could be lowered dramatically. Instead of needing the mass energy of the universe, perhaps only the energy of a few stars would suffice. This was still impossibly large, but it was less absurd, a step from fantasy toward faint feasibility. The team even constructed small laboratory experiments, attempting to detect tiny distortions of space-time with interferometers. These experiments were modest, probing minute scales, but the symbolism was enormous. For the first time, warp was not only a story told on television or an equation on paper. It was a research project. However tentative, inside NASA itself, headlines declared that the agency was exploring warp drives. Critics were quick to point out that nothing tangible had been achieved, but the psychological leap was undeniable. The dream had entered the halls of serious institutions. Outside NASA, theoretical physicists continued to refine the idea. Papers explored ways of reducing energy requirements further, of stabilizing the bubble, of reconciling it with quantum field theory. Each refinement chipped at the mountain, lowering the demands from galaxies to stars to perhaps planets. Still immense, still unattainable, but no longer infinite. The mere act of exploring the concept enriched physics, forcing deeper questions about space-time, energy, and the role of exotic matter. Even if warp never leaves the blackboard, the search for it illuminates the frontier where relativity and quantum theory meet. The question of dark energy looms large in this frontier. We already know that the universe is expanding, and not just expanding but accelerating. This acceleration is driven by something mysterious, a pressure woven into space itself that we call dark energy. It accounts for nearly 70% of the cosmos, yet its nature is almost entirely unknown. If dark energy can accelerate galaxies, perhaps it can be harnessed, focused, and controlled. Perhaps it is the raw material warp requires, the exotic stuff that can bend space in ways we cannot yet imagine. Some even speculate that warp is already happening on cosmic scales, written into the accelerating universe. The challenge is whether we can localize it, compressing the expansion of billions of light years into a bubble around a ship. The other great hope lies in quantum gravity, the long-sought unification of general relativity and quantum mechanics. At present, the two frameworks are disjoint. Relativity describes the large scale, quantum mechanics the small, and at the Planck scale, where both should merge, our theories falter. A complete quantum theory of gravity may reveal new structures of space-time, new ways energy and geometry interact. It might show that negative energy is more accessible than we think, or that space-time itself can be engineered in ways we have not yet conceived. Until such a theory is built, warp remains suspended between possible and impossible. The future of faster-than-light dreams is therefore not a matter of engineering but of discovery. The rockets and reactors of today cannot bring warp any closer. What is needed is a revolution in understanding, a new physics as transformative as Einstein's was a century ago. If such a breakthrough arrives, it may bring with it the tools to shape space-time deliberately. If it does not, warp will remain a mirage, a symbol of longing that guides, but never delivers. The uncertainty is vast, but so too is the possibility. Why then does the dream persist, when the barriers remain so towering? The answer is as much human as it is scientific. Distance is our greatest prison. Even the nearest star beyond the Sun, Proxima Centauri, is more than 4 light-years away. With the fastest probes we have built, the journey would take tens of thousands of years. For a species whose recorded history barely spans 5,000, such timescales feel indistinguishable from never. Without faster-than-light travel, the stars remain ornaments in our sky, unreachable, no matter how bright their invitation. Warp, wormholes, or some future geometry of space-time are the only paths that promise to shatter this confinement. The pursuit of these dreams is therefore not folly, but necessity. Without them, the universe shrinks. Exploration ends at the edges of the solar system. Civilization remains confined to a single star, vulnerable to its rhythms and catastrophes. The sun will not burn forever. Asteroids and comets still drift through space, silent threats that care nothing for our ambitions. To remain bound to Earth is to gamble with extinction. To break the light barrier, even in the indirect way warp proposes, is to seize a chance at survival. The dream is not only wonder, it is insurance against the silence of eternity. Yet this same motivation collides with the stubbornness of physics. Every attempt to refine warp metrics, every proposal to stabilize wormholes, every calculation of energy or causality returns us to the same conclusion. The dream is possible only in equations, not in practice. Negative energy cannot be harnessed in useful amounts. Instabilities lurk in every geometry. Radiation builds to catastrophic levels. If the laws of the universe contain safeguards against paradox and destruction, then warp may be mathematically allowed, but physically forbidden. It may be that the stars are forever beyond our reach, not by distance, but by decree. Still, the effort has value. Every exploration of warp teaches us more about space-time. By pushing Einstein's equations to their extremes, physicists learn where the boundaries lie, where relativity bends and where it breaks. Studies of exotic matter sharpen our understanding of quantum fields. Investigations into wormholes illuminate the puzzles of black holes. Even failure enriches science. Warp may never fly, but it pulls us toward deeper truths. Dreams have always done this. The dream of flight preceded airplanes. The dream of the moon preceded rockets. The dream of warp may precede something else, something we do not yet have words for. There is also the cultural dimension. Science fiction has primed us to imagine warp not as an abstraction, but as a lived possibility. From the bridge of the Enterprise to the spice-laden sands of Arrakis, warp and its cousins are woven into our collective vision of the future. These stories matter. They inspire the engineers who build probes, the physicists who write equations, the agencies that fund exploration. Without them, perhaps no one would have looked twice at Alcubierre's paper. Fiction breathed life into the mathematics, and mathematics returned the favor by legitimizing the dream. Together they form a cycle of imagination and inquiry that drives human progress. So we arrive at a paradox of our own, not in physics but in philosophy. Warp is both impossible and indispensable. The equations allow it, but the universe resists. The hazards are staggering, the energy demands absurd, and yet the vision refuses to die. Humanity continues to probe, to refine, to imagine. Perhaps we are chasing a mirage, or perhaps we are inching toward a horizon we cannot yet see, where a deeper understanding of space-time will turn mirage into path. The truth may not be warp as Alcubierre described, but something stranger, born from quantum gravity or dark energy, waiting to be discovered. The future of faster-than-light travel rests on a knife's edge between wonder and denial. On one side stands the dream, sharpened by equations and fired by imagination. On the other stands the resistance of physics, the barriers of energy, causality, and hazard that seem unyielding. For every refinement that lowers the requirements, a new obstacle appears. For every speculative hope, a sobering calculation arrives. The future may hold warp as destiny, or it may hold warp as eternal mirage, a symbol we chase but never catch. Some physicists argue that impossibility is the likeliest verdict. The laws of nature, they say, are not cruel but consistent. Light speed is a limit because it preserves causality and stability. Negative energy appears in whispers but vanishes when scaled. Quantum field theory resists violations of its energy conditions. The universe may allow warp in mathematics, only to remind us that not every equation can be built. Just as perpetual motion machines are forbidden by thermodynamics, warp drives may be forbidden by the deeper logic of space-time. To search for them may be noble, but the answer may always be no. Others resist such finality. They point out that history is littered with impossibilities overturned. Heavier than air flight was once deemed absurd. Space travel was dismissed as fantasy. Even quantum mechanics, with its probabilities and entanglements, was once considered madness. Physics progresses not by affirming limits, but by discovering new frameworks that transcend them. Perhaps warp requires not defiance of relativity, but its completion. Perhaps quantum gravity will show us that space-time is not continuous but foamy, filled with structures that can be harnessed. Perhaps dark energy will reveal itself not as a mystery to be endured, but as a resource to be shaped. The future may hold answers, stranger than any we imagine. Between certainty of impossibility and certainty of discovery lies humility. We do not yet know. We cannot yet know. The questions warp raises about energy, causality, space-time, and survival reach beyond our present science. They point toward the next revolutions, the next Einsteins, the next frameworks, waiting to be written. Whether warp becomes real or not, the pursuit itself is valuable. It forces us to test the limits of knowledge, to confront the boundaries of imagination, and to remember that science is not only about what is, but about what might be. For humanity, the dream is not trivial. It is tied to our destiny among the stars. If warp remains impossible, then interstellar travel will belong to probes, patient machines crossing gulfs over millennia. If warp becomes possible, then the galaxy itself may become our frontier. The difference is nothing less than whether we remain a planetary species or become a galactic one. No other dream carries stakes so vast. So we stand at a crossroads, gazing at equations that permit and realities that deny, imagining futures where warp lifts us to the stars, or remains forever out of reach. The future of faster-than-light travel is not yet written. It may never be written, but its very uncertainty ensures that the dream will endure. For as long as we look up at the stars and wonder, the question will remain alive. And so we turn to the final judgment. Has warp truly beaten the speed of light? Or has it only danced at the edges of possibility? Does it offer a path through the cosmic barrier, or is it an illusion crafted by mathematics and sustained by hope? The answer lies in the balance between science and imagination, between law and loophole. The final verdict awaits. The journey began with a limit. Einstein revealed that light speed is not just a number, but the boundary of motion, the thread that preserves causality and order. To approach it is to fight against infinity. To cross it is to demand what the universe cannot give. Time slows, lengths contract, energy soars beyond reach. Light speed is not merely fast, it is sacred, the keystone of space-time. Humanity, gazing at the stars, discovered not freedom, but confinement. And then came Alcubierre. With a handful of equations, he showed that relativity contained a loophole. If one could not outrun light within space-time, perhaps one could reshape space-time itself. His warp bubble was not rebellion, but reimagination, not a hammer against the wall, but a door in its surface. Expansion behind, contraction ahead, a pocket of stillness carried faster than light, without breaking the rules. It was audacious, elegant, and intoxicating. Suddenly, the prison of distance seemed less final, but the door carried its own locks. The energy required was beyond comprehension, demanding negative matter, in amounts rivaling planets or stars. Later, refinements lowered the price, but it remained astronomical, far beyond the reach of any civilization we can conceive. Even if the energy could be found, hazards loomed. Radiation piled at the bubble's prow. Instabilities threatened collapse. Control and communication were severed by geometry itself. A ship at warp might reach its destination only to destroy it, or itself, in the very moment of arrival. Warp was not merely impossible, it was dangerous, and beyond energy and hazard lay causality. Faster than light, travel twists time as much as space. Closed time-like curves, paradoxes of cause and effect, the spectre of chronology undone, all followed in warp's wake. Hawking warned that the universe would defend its own coherence, that any attempt to break chronology would collapse in a storm of quantum radiation. Perhaps the laws of physics themselves forbid warp, not only to preserve light speed, but to preserve logic. If so, the equations permit what the universe denies. Warp would remain a mirage, a shadow on paper, with no echo in reality. Yet to dismiss warp entirely is to ignore what it has given us. It has sharpened understanding of relativity, inspired experiments, drawn attention to dark energy, and forced us to confront the deepest puzzles of space-time. It has reminded us that physics is not finished, that our theories are incomplete, that possibilities may lie hidden beyond horizons we cannot yet see. Even as an impossibility, warp enriches science. Even as a dream, it guides discovery. For humanity, the verdict is therefore not only scientific, but symbolic. Warp may never lift us to the stars, but the desire it embodies will endure. It is the desire to refuse confinement, to challenge limits, to imagine futures beyond the present horizon. Light speed may remain absolute, but imagination is not bound by kilometers per second. Every equation we write, every telescope we raise, every dream of faster-than-light travel is part of the same defiance. We look at the stars and say, not yet, but one day. The final verdict must therefore begin with honesty. Warp does not beat the speed of light. It cannot erase the cosmic limit or allow us to rush past it, as fiction suggests. What it offers is something subtler, stranger, and more profound. It sidesteps the limit by bending the very stage on which the race is run. It does not let us sprint faster. It lets us fold the track. In this way, warp honors light, even as it seeks to outwit it. To render judgment on warp is to weigh two truths. The first is that physics, as we know it, sets barriers that appear insurmountable. Energy requirements tower beyond possibility. Hazards threaten destruction, and causality trembles under the weight of paradox. The second truth is that physics, as we know it, is not complete. The universe hides mysteries as profound as those Einstein revealed a century ago. Dark energy accelerates galaxies. Quantum entanglement binds particles across space. Black holes conceal singularities where space-time itself dissolves. If limits exist, they exist within a framework that may itself be temporary. Warp lives in the space between those truths. It is an illusion in practice, yet a beacon in theory. It shows us what relativity permits, even if the universe refuses to cooperate. It whispers that space-time is pliable, that distances are negotiable, that impossibility is not always absolute. It does not deliver faster than light travel to our hands, but it reminds us that imagination can pry open cracks in the wall of reality. In this sense, warp has already achieved something extraordinary. It has transformed the impossible into the conceivable, the unimaginable into the discussable. The verdict also belongs to humanity's relationship with dreams. Throughout history, we have imagined futures that seemed unattainable. For centuries, flight was reserved for birds and gods. Then came wings of wood and cloth, fragile yet triumphant. Space itself was once the domain of myth. Then came rockets, fragile towers of fire, carrying us beyond the atmosphere. Each impossibility toppled, not by defying physics, but by understanding it more deeply. Warp may stand in that same lineage, awaiting a new framework, a new discovery, a new way of seeing, or it may remain forever beyond reach, a symbol rather than a reality. Both outcomes carry meaning. Even as a symbol, warp challenges us. It forces us to look at the stars, not as ornaments, but as destinations. It forces us to confront the scale of the universe and the fragility of life confined to a single world. It forces us to accept that survival may one day depend on transcending the barriers of distance. Whether warp is real or not, the need it expresses is real. The desire to roam the galaxy, to endure beyond the lifespan of Earth and Sun, to find our place among the stars, is as essential as breathing. Warp embodies that desire in equations, giving shape to hope. There is also humility in the verdict. Light speed is not a challenge to be conquered lightly. It is not a wall to be smashed, but a law to be respected. Einstein did not place it there. The universe did. Warp, if ever realized, will not erase that law, but work within it, sidestepping rather than shattering. This is the deeper lesson. Nature is not easily outwitted. The laws of physics are not obstacles to be broken, but structures to be understood. Warp teaches us that ingenuity lies not in rebellion, but in reinterpretation. So the verdict is not simple. Warp does not beat light. It does not give us a clear path to the stars, but it does not vanish into impossibility either. It remains a liminal idea, poised between fantasy and physics, a mirror reflecting both our ignorance and our potential. Perhaps that is enough. Perhaps the role of warp is not to carry us to other worlds, but to remind us that the universe is stranger than we think, and that our greatest journeys begin not with engines, but with questions. In the end, the question was simple. Can warp speed really beat the speed of light? The answer, after all the equations and paradoxes, is no. Light speed is not conquered. It remains the boundary, the constant, the pulse of the universe. Warp does not break it. Warp does not outrun photons in their own domain. Warp cheats in another way, bending the field rather than crossing it, reshaping the map rather than redrawing the path. Light speed is law, warp is loophole. But this distinction, far from trivial, carries the weight of destiny. To accept the law is not to surrender to confinement. It is to seek new routes within the boundaries of what is possible. Humanity has always done this. We did not sprout wings to fly. We learned aerodynamics. We did not grow gills to breathe underwater. We built vessels that carried air with us. We may never outrun light, but we may learn to ride the curves of space-time, to sculpt geometry as nature does with stars and black holes. Warp, even if it never flies, is the name we give to that hope. So the final verdict is twofold. Scientifically, warp remains a speculation, permitted by relativity, but strangled by energy demands, hazards, and paradoxes. It is not a working technology. It may never be. But symbolically, warp is humanity's challenge to the cosmos, our refusal to bow to distance, our determination to reach beyond what seems final. It is the mathematics of hope, the physics of imagination, the science of longing. If one day we master it, we will not have outrun light. We will have reshaped reality itself. The cosmos will no longer be a vast prison of distance, but a malleable field of possibilities. The stars will not be ornaments but neighbors. The galaxies will not be unreachable but open roads. Warp will not erase light speed. It will honor it by finding the cracks in the law and turning them into pathways. Until that day, warp remains a story written in equations and whispered in dreams. Light speed is nature's decree. Warp speed is humanity's reply. The cosmos is vast, but so is imagination. Perhaps one day the two will meet. Until then, the verdict is clear. Warp does not beat the speed of light. It redefines what it means to race at all.